What if I told you a time machine already exists? Sort of. And you've probably seen one without even realizing it. We're talking about MRI scanners, the ones in hospitals. So the big question for today is, can these incredible machines actually turn back the clock?
The source material for this explainer has this beautiful line. It says an MRI is like listening to the memory of matter. I love that. It's not just snapping a picture of your insides. No, it's tuning in to this cosmic story of order giving way to chaos, or entropy. It's literally picking up an echo from the past.
Okay, so that brings us right back to our central question. When we hear this echo, are we actually reversing time, even for just a split second? Or is there something weirder, something deeper happening down at the quantum level?
All right, to get to the bottom of this, we need to talk about what this echo really is. It's a specific phenomenon called a spin echo. And honestly, it's the key to this whole puzzle.
So what is a spin echo? Well, it's pretty much what it sounds like. Imagine shouting into a canyon. Your voice travels, fades away, and then boom, it comes back as an echo. The spin echo is the same idea, but with a radio signal inside an MRI. It completely disappears, and then, like magic, it reappears. The real question is, how on earth does it do that?
Okay, so it's not actually magic. It's just some incredibly clever physics. It all comes down to a super precise four-step dance of radio frequency pulses that mess with the atoms inside you. Let's walk through it step by step.
Okay, this is the whole shebang right here, the four-step sequence. First, step 1. We hit the atoms with a 90-degree radio frequency pulse. Zap! This basically knocks all their tiny nuclear spins over, so they're all lined up and spinning in a flat plane. Nice and orderly, but, order never lasts. That brings us to step 2, dephasing. The spins immediately start to fall out of sync. A great way to think about this is like runners at the start of a race. The gun goes off and they all start to spread out. The fast ones get ahead, the slow ones fall behind. As they all drift apart, the signal we're trying to measure just fades to nothing. It's gone. Now, here comes the brilliant part, step 3. We hit them with another pulse, but this one is a 180-degree pulse. What does that do? It's like a command that tells all the runners to instantly turn around and run back towards the starting line. All of a sudden, the fastest runners who were way out in front are now at the very back of the pack, and the slower ones are now in the lead. And that perfectly sets up the grand finale, step 4, rephasing. Because the fast runners are now at the back, they have a chance to catch up to the slower ones. And for one single perfect moment, they all arrive back at the starting line at the exact same time. They're perfectly aligned again, and right at that moment of realignment, they release a burst of energy. And that's it. That's the spin echo we detect.
So when you see that, right, a signal vanishes into chaos and then perfectly reappears, it really feels like you just watched time go backwards. It looks like we just unshattered the glass. But did we? Did we actually just break a fundamental law of physics?
Well, you probably guessed it. The answer is no. As amazing as the spin echo is, it's not actually breaking the arrow of time. Let's dig into why our physical reality is a lot less flexible than the math on a blackboard.
See, here's the thing. On paper, in the pure world of math, the quantum equations that describe those spins work perfectly fine forwards and backwards. But we don't live on paper. We live in the real world. And out here, we have rules, big ones, like entropy. The reason your coffee gets cold and a broken egg never puts itself back together. And causality, the rule that says you have to trip before you fall. Those rules lock time's arrow, pointing it firmly in one direction, forward.
This is really the key to understanding it all. The reversal we're seeing isn't a reversal of the clock on the wall. It's happening in something physicists call phase space. What does that mean? Well, think of it like this. We're not rewinding the tape of reality. We're just cleverly reorganizing the positions and directions of our runners to make them cross the finish line together again. The whole process, from the first pulse to the final echo, is still marching forward in time, playing by the rules of physics, specifically the forward time block equations. Yeah, at the end of the day, it really comes down to a couple of unbreakable rules of reality. First, the second law of thermodynamics. It just says that on the whole, things always get more disordered, never less. And second, relativity. You can't go faster than light, and you can't send a message to your past self. The spin echo is genius because it finds a way to create an illusion of reversal without actually breaking any of these fundamental laws. So, okay, if it's not a time machine, then what is it? What are we actually seeing when that echo appears? Well, it's something almost as cool. A perfect simulation of time reversal.
The source material has a great way of putting it. Don't think of the MRI as a wormhole to the past. Instead, think of it like a perfect digital movie file. It records the exact state of all those little atomic spins, and then it can effectively hit rewind on their orientation to play it back for us. It lets us see what time reversibility would look like without ever actually violating the laws of time.
And that right there is the big takeaway. The spin echo is like a little window into the bizarre world of quantum mechanics, where things can be reversible. But it also shows us that the moment you zoom out to our big, messy, everyday world, time's arrow is locked in. It only goes one way.
So let's be super clear. No, an MRI is not going to send you back to the 90s. But what it does do is maybe even more important. It gives us a real physical lab to explore that fuzzy boundary between the quantum world where time can be flexible and our world where it isn't. It's a tool for studying the nature of time itself.
And that leads to a really exciting final thought. If we can get this good at simulating time reversal, what else can we do? I mean, this very technique is the bedrock for things like quantum memory and quantum computers. By mastering these time echoes, we are literally paving the way for a future of technology that is hard to even wrap our heads around. It turns out, we're not just listening to the memory of matter anymore, we're starting to learn how to write it.